Okay, we're going to venture into Chapter 21 and a little bit of statistical mechanics, the kinetic theory of gases. We can think of macroscopic gas properties, properties of state variables, such as pressure, volume, temperature, even internal energy if we wish. We can relate that to actually the microscopic properties of the gas on a molecular scale if we do some kind of mathematics. We're going to treat the matter as a collection of molecules. Newton's laws of motion will still be applied, but it will be applied statistically to all these molecules as a whole. This kinetic theory will provide us with a physical basis for understanding the effects of temperature and internal energy of the gas. We're going to start with an ideal gas and make some assumptions of this ideal gas. The gas molecules themselves are very small. Molecules obey Newton's laws of motion. As a whole, they move randomly, but if we apply forces on the gas, then as a whole, they will move according to those forces and in a collective sense. All collisions are elastic. Hence, kinetic energy will be conserved in every collision. Kinetic energy will be constant for this gas. The forces between molecules are negligible, so we're not going to have any kind of individual interactions between the molecules themselves, except during a collision, and only for the collision where kinetic energy will be conserved. And all molecules will be identical, hence we'll have a pure gas. We have an ideal gas, and in terms of molecular and atomic is more closely related to ideal gas, but even on a molecular scale where we might have a diatomic or polyatomic gas, it can act like this ideal gas if we're at low pressures and low temperatures. So molecular rotations and vibrations will have no particular effect on our translational motions. All right, so consider a molecule contained in a cube of edges of length d. So our cube is d, d, and d in x, y, and z dimensions. And we're going to have a collision of this molecule with a wall. We'll assume that these collisions are perfectly elastic so that we aren't losing any energy with these collisions, and kinetic energy will be conserved within the gas itself. Let's just look at an x component of one of these collisions colliding, say, with the right-hand wall. Our momentum going in is going to be the mass of the molecule times its x component of velocity, v sub x. It collides elastically with the wall, hence its rebound velocity will have a magnitude v sub x and a momentum negative m v sub x. So the change of momentum of this molecule with the wall will be mass times our final velocity minus mass times our initial velocity. That will be a negative m v sub x minus m v sub x, or a change in momentum of a negative 2 times mass v sub x. And for that matter, the wall will have a change in momentum of the positive of this value, 2 times mass v sub x. In order for the same molecule to make a collision with that same wall, it must travel all the way, bounce off the opposite wall, and then come back again. So it must travel a distance d across this cube, and then d back again to hit the same wall. That's going to take time, and the time it's going to take is going to be the time it takes traveling at v sub x to go a distance 2d. So the time between collisions is going to be equal to that distance, 2d, divided by its x velocity, v sub x. Hence, the average force exerted on the wall by a molecule is going to be this change in momentum, 2m v sub x, divided by this delta t that we just calculated. That's going to be 2m v sub x times v sub x divided by 2d, or mass velocity x squared divided by d. Bear with me, we're headed somewhere with this. Note that the average value of the square of the velocity in the x direction for all n molecules is equal to the x velocity squared for all these individual molecules add together divided by the number of molecules we have. So that would give us an average velocity of the x velocity squared for all these molecules. So the total force on the wall by n molecules on this wall is going to be m divided by d, number of molecules, times this average x squared velocity for all these molecules together. Any particular molecule will actually have three velocity components, x, y, and z. So our velocity squared by the Pythagorean theorem will be v sub x squared plus v sub y squared plus v sub z squared. And since all these directions, x, y, and z, are equivalent in a sense for random motions, so v sub x squared equals v sub y squared equals v sub z squared individually, we can say that our average velocity squared for these molecules is equal to 3 times any individual component, say v sub x squared on the average. So in terms of our velocity squared on the average for any particular molecule, we can write our force as mass divided by d and our average velocity, or average of the velocity squared, divided by 3. And then substitute n. So we have n divided by 3, mass velocity squared on the average divided by d. So our pressure on this wall with the area of d squared will be force per area, force divided by d squared. We'll take this force up here, divided by d squared, and we get 1 over 3 n divided by d cubed, mass times velocity squared on the average, which we're going to factor out a 2 here. So I got 1/3 n divided by d cubed, but d cubed is the volume of this cube. So we have n divided by the volume, 2 times 1/2 mass times our velocity squared on the average. So it's 2/3 number of molecules divided by volume, 1/2 mass times the velocity squared on the average. Rearranging this, we have that the pressure times the volume is equal to 2/3 number of molecules, 1/2 mass times the velocity squared on the average. This 1/2 mass times the velocity squared on the average is our average kinetic energy of that molecule. We'll compare this to the ideal gas equation in the form PV equals nk Boltzmann T, and we can see that our average kinetic energy per molecule, 1/2 mv squared average, is equal to 3/2 k Boltzmann T. So our average translational kinetic energy per molecule of a monatomic gas is proportional to temperature by the PV equals nRT. This is really interesting. So our average kinetic energy of a molecule of ideal gas is equal to 3/2 k Boltzmann T. Two major conclusions based on this. We can relate our macroscopic result, average kinetic energy, internal energy, and in this case the pressure on the wall, from the microscopic contribution of many molecules, just dealing with them statistically. Also, the temperature is a direct measurement of the average molecular kinetic energy. So the internal energy of ideal gas depends only on its temperature. Also note that since our average of our x velocity squared is equal to 1/3 of our total velocity squared on the average, we can prove that our translational kinetic energy in the x direction, 1/2 m v sub x squared on the average, is equal to 1/2 k Boltzmann T. And for equivalently, since we have randomness in all directions, x, y, and z, 1/2 mass times the velocity y squared on the average is 1/2 k Boltzmann T, and so is 1/2 mass times the velocity z squared on the average, 1/2 k Boltzmann T. So all these kinetic energies in the x, y, and z individually is equal to 1/2 K Boltzmann T. So each direction represents what we call a translational degree of freedom, and each translational degree of freedom has associated with it an energy of 1/2 K Boltzmann T. This brings us to the theorem of equal partition of energy. Each degree of freedom in a system contributes 1/2 K Boltzmann T to the energy of that system, where we have possible degrees associated with, in this case, translation, 3 degrees associated with our x, y, and z directions, x, y, and z. We possibly could have rotation, 2 degrees of freedom for molecules in terms of rotation, and vibration, 2 degrees of freedom associated with vibration for molecules as well. So in terms of translation, 3 degrees of freedom. So our kinetic energy in terms of translational monatomic kinetic energy, it would be 3/2 K Boltzmann T with 3 degrees of freedom. And our other degrees of freedom, if we had a molecule, we'd have 2 degrees of freedom for rotation, especially in the directions where we're not along the axis of the molecule itself. Basically, negligible energy in terms of rotation along the axis. Along the other 2 axes, 2 degrees of freedom and 2 values of 1/2 K Boltzmann T from those. For vibration, another 2 degrees of freedom, and we have a degree of freedom associated with your understanding of the equal partition theorem, so an extra degree of freedom associated with that. No, just kidding. So we have 2 degrees of rotation, 2 degrees associated with vibration, and 3 degrees associated with translation, x, y, and z. The total translational kinetic energy of n molecules of an ideal monatomic gas in 3 dimensions will be the number of molecules times 3 times this 1/2 K Boltzmann T, which will be 3/2 n K Boltzmann T. So that's the total energy of n gas molecules. Well, note that K Boltzmann is 1.38 times 10 to the minus 23. If I multiply this by Avogadro's number, 6.022 times 10 to the 23. As we multiply it, the 10 to the minus 23 and 10 to the 23 cancel out. And 1.38 times 6.022 is our R gas constant, 8.31. How about that? So R is equal to K Boltzmann times Avogadro's number. Our total number of molecules is the number of moles times Avogadro's number. So the number of molecules times K Boltzmann is equal to the number of moles times Avogadro's number times K Boltzmann, which we could write as the number of moles times Avogadro's number times K Boltzmann, but we just proved that K Boltzmann times Avogadro's number is our gas constant R. So the number of molecules times the K Boltzmann constant is the number of moles times our gas constant R. We can substitute that in to our total energy of n gas molecules. And with that substitution, we get that the energy, the total energy of n moles of an ideal monatomic gas is 3/2 number of moles, little n, R, 8.31, times the temperature. If we had a diatomic molecular gas at room temperature, we have the rotational modes as well, so we have 2 more degrees of freedom, and hence the total energy of a ideal diatomic gas at room temperature, molecular gas, is 5/2 nRT, with the extra 2 degrees of freedom. Note since 1/2 m velocity squared on the average is 3/2 K Boltzmann T, that's our average kinetic energy, translational kinetic energy. If I multiply both sides by 2, solve for the velocity squared on the average, I get 3 K Boltzmann T divided by the mass. I'm going to multiply this by Avogadro's number on top and bottom. So K Boltzmann times Avogadro's number will give us the R constant. The mass times Avogadro's number will give us the molecular molar mass. So we have the velocity squared on the average is 3RT divided by the molar mass of the gas. We often speak of the root mean square value of the velocity. This is the square root of the mean value of the velocity squared. Here I have the velocity squared and the average value or the mean value. Don't know why we don't talk about the nice value. But we have the mean value of the velocity squared, and we take the square root of it. We have our root mean square velocity. So the root mean square velocity square root of v squared on the average, and that's going to be equal to the square root of 3RT divided by the molar mass m. Here are some root mean square speeds at room temperature for some gases. If we have hydrogen at room temperature, a molar mass of 2 times 10 to the minus 3 because it's a molecule, and we have a root mean square velocity at 20 degrees Celsius, which would be 293 Kelvin, of 1902 meters per second. Helium, which is a monatomic gas, has a molar mass of 4 kilograms per mole. So we have to use kilograms per mole for our molar mass, and have to make sure we know whether it's monatomic or diatomic. Has a root mean square velocity at 293 Kelvin of 1352 meters per second, and so forth and so on. So we have to put in the molar mass in terms of kilograms per mole for all of these gases, realizing things like nitrogen, which has a molecular weight of 14, but a molar mass in terms of molecule N2 will be 28 times 10 to the minus 3 kilograms per mole. Let's try out a problem with this. The temperature near the top of the atmosphere on Venus is 240 K. Find the root mean square speed of hydrogen at this point in the atmosphere. Even though these gases are polyatomic, they're not monatomic. They act like monatomic gases translationally at these low temperatures. So we don't have the rotational modes and definitely don't have the vibrational modes. So at this low temperature, the velocity, the root mean square velocity is going to be equal to the square root of 3RT over the molar mass of hydrogen. That's going to be 3 times the gas constant, 8.31, at 240 K. And our molar mass in terms of kilograms per mole, because we have 2 hydrogens, that's going to be 2 kilograms per mole, or 2 times 10 to the minus 3 kilograms per mole for hydrogen. That gives us 1,730 meters per second for the root mean square velocity of hydrogen in the atmosphere of Venus. We're going to repeat this for carbon dioxide. The molar mass of carbon dioxide, carbon is 12, oxygen is 16. So we have 2 oxygens. 16 plus 16 is 32, plus carbon, which is 12, gives us a molecular weight of 44. And so for carbon dioxide, our molar mass will be 44 times 10 to the minus 3 kilograms per mole. And hence, our root mean square velocity in this atmosphere is 369 meters per second. It's been found that if the root mean square speed exceeds 1/6 of the planet's escape velocity, the gas will eventually leak out into out of the atmosphere and into outer space. If the escape velocity on Venus is 10.3 kilometers per second, does hydrogen escape and does carbon dioxide escape? Well, let's check this escape velocity. From Physics 1, we have that the escape velocity of a planet like Venus is 2g, mass of the planet, or the radius of the planet. For Venus, the mass is 4.88 times 10 to the 24 kilograms, The radius of Venus is 6.06 times 10 to the 6 meters. Of course, the gas, or G constant, is 6.67 times 10 minus 11. So that is indeed 1.037 times 10 to the 4 meters per second. 1/6 of this speed is going to be 1,727 meters per second. The root mean square velocity of hydrogen just exceeds this, so the hydrogen will escape eventually out into outer space from Venus. There won't be any hydrogen in Venus's atmosphere. But carbon dioxide, a greenhouse gas, is too small of a root mean square velocity to reach this escape speed, and hence it will be retained in the atmosphere, hence build up, making Venus a very greenhouse type place and a very hot place indeed. So that concludes our first lecture in Chapter 21, dealing with statistical mechanics and the kinetic theory of gases.